Okay, in this video I'm going over how to derive the total surplus that we get from adding an if and only if contract of the form that we're looking at to solve public goods problems with a blockchain. So, this is analogous to the game theory matrix, payoff matrix here. So I want to connect each step in the model building to what it looks like when we're looking at this simple payoff matrix. So we know that we started out without the if and only if option, in which case we just had our four square prisoner's dilemma. The case I'm going to think about here is two companies that would like to build on an infrastructure for collecting data or for acting as an interface to users, something along those lines. I mean, the simplest way to think about this is self-driving car data. We want all the people who are inventing self-driving cars to pool their data and to build the best and safest self-driving cars possible. We don't want to divide all of that data up among them because they're going to have less data to make those cars safe. So if they're collaborating, if these competitors are collaborating in a horizontal blockchain consortium, how do we think about the surplus from the existence of that consortium? Because we want to make sure that we divide the spoils among the different companies. In our case, there's only going to be two companies just to keep things simple. How are we going to divide the surplus among them? Well, the first step in that is to actually measure or think about how do we estimate that surplus. In this case, we have the options to invest in this blockchain consortium that collects more data about people's driving habits, or to not invest in that. And of course, the Nash equilibrium, if we're just looking at the four square payoff matrix that's the prisoner's dilemma, the Nash equilibrium will be for both companies to not invest in that infrastructure for collecting the data. But of course, they'd be better off if they both invested, in which case they'd both get a payoff of 9 as opposed to 4. Classic prisoner's dilemma. We added on top of that the option to invest if and only if the other players in the consortium invested, in which case the addition of this is what the blockchain consortium brings. It's this smart contract that automatically executes and automatically enforces both players investing an upfront amount in order to make this happen. So if we want to know what's the surplus from the existence of the if and only if contract, we look at what's the equilibrium without the if and only if option, in which case the Nash equilibrium is 4 plus 4, it's 8. When we have the if and only if outcome, we have a second Nash equilibrium, which is better Nash equilibrium, which is 9 and 9, so the total welfare in that case is 18, in which case the surplus from the existence of the if and only if contract is 10. And if the companies are symmetric, and if we have perfect information about their cost structures and their payoffs, dividing this equally might be a fair way of dividing it. But of course, we're going to have to build smart contracts that take into account negotiation power. There could be, the companies could exercise power similar to union power from the past. So we'll eventually need to think about those things. For now, we're just going to model the simplest possible scenario. We're going to try to take this scenario and turn it into a model version where we have demand equations and things like that. So the first thing we'll model will be the duopoly. And the duopoly will be analogous to the case where the Nash equilibrium is here and neither player invests. So let's start out, we've got a duopoly. And the analogy of don't invest, don't invest. And our duopoly has two players who are competing against one another, so they set up their optimization problems. In this case, the choice is how much to invest, and of course that's the advantage of having a model over having a payoff matrix like this. Here you only have the options invest, don't invest. When you have models, you can actually ask the question, how much money is each player going to invest? And we're going to have number of users, so I should label these investment. And of course that's from player 1. Number of users of player 1's website or player 1's self-driving car, whatever they happen to be. And number of users depends on the investment from company 1 and also the investment from company 2, because the collection of that data is a public good. It's a shared resource. And there's a price that they charge per transaction. Price per transaction. So this model is going to be a classic platform model where we have number of users, price per transaction, and percent of transactions or share of transactions. Share of transactions that are saleable. You can actually charge some amount of money for. And then we keep the cost really simple minus the investment cost. So this is one player's model. Now, of course, the other player is going to have an identical model except replacing all of the sub 1s with sub 2s. So here's our first player's optimization problem, here's our second player's optimization problem, and they're symmetric. So that's the case in the duopoly, in which case the total welfare, and this is welfare between the firms, in the duopoly, is after you've solved these two models. Let me mark the exogenous variables here. Those are the exogenous variables. So you solve these two models, you take the first order conditions, and you get, let me use a different color for this, you get out of those models first order conditions that gives you I star 1, the optimal investment given the other player's investment. So you solve it for both models, first order conditions, yada yada yada, and we get I star 2. And of course, I star 1 is a best response to player 2's investment. And player 2's investment is a best response to player 1's investment. That's the way Nash equilibrium looks when we're using it in a modeling setting. So the optimal amount of welfare, or the total welfare at the end of this, is going to be the total profit of one player when you plug in this and this. We're basically taking the profit from one, profit from the other, and adding them up, plugging in the optimal choice as a best response to each other. So it's somewhat boring, but I'm going to go ahead and write that out. Okay, so this just says the payoff, total payoff in this duopoly is the profit of the player 1, where we're plugging in I1 and I2, plus the profit of player 2. That's the total welfare. Now we need to compare that to the total welfare in the case where they're using an if and only if statement, in which case, how do we calculate that? So our next step is to calculate the monopolist situation. And the monopolist situation is going to be analogous to both players investing where they're cooperating. So they're basically behaving like a monopolist firm that's maximizing the total profit among the industry, and then it'll have to figure out how to divvy up that profit among the players. So we have a monopolist, which is like the consortium, basically. And then the analogy when we look at this table is going to be both players investing, invest. Okay, so to do that, we're going to maximize by choosing total investment in the industry, that's investment from both players added together. And the payoff from both players is going to be first, the profit from from company number 1, which is the number of users as a function of the investment in that platform times the price per transaction for company 1 times the share of transactions for company 1 that are saleable minus, plus This is total revenue for firm 1 plus total revenue for firm 2, which is the number of users from firm 2 as a function of the total investment times the price per transaction for firm 2's users times the percentage of transactions that are saleable for firm 2 minus the investment. So this is the total welfare among both firms. In which case we're going to take the first order conditions, and that's going to give us an optimal I star total investment from both firms. So the total welfare in the monopolist state, and this is of course analogous to the 18, the total welfare that we had when both firms cooperated when we ended up down there. This is going to be simply the total profit at the optimal I star. So this is, it's a little bit boring, but I'm going to rewrite this whole profit function just with I star, and it should be analogous to this duopolist profit. So okay, so let's remind ourselves what these represent. This is welfare in a monopolist state, and this is welfare in a duopolist state. And of course we know a monopolist's welfare is going to be greater than a duopolist's welfare because they're sort of picking the exact perfect amount of investment for the total industry. So if you take this minus this, that's going to give you the surplus from the existence of the if and only if contract. So that's analogous to the 10. The fact that we were subtracting 8 from 18 to get 10, to get how much do we benefit going from a prisoner's dilemma situation to a well-enforced contract situation that blockchains can bring us through smart contracts. And that's basically how you come up with the total surplus. Now, once you've come up with this, you need to start asking some other questions. This modeling has assumed we have perfect information. It's assumed we have symmetric firms, so it's easy to just divide the surplus in two. But those can be difficult questions. How do you actually estimate somebody's cost structure? For example, this is something akin to a demand function. How do you estimate that demand function for the different players? What if players try to cheat in representing themselves in their particular demand functions in order to get a greater share of the pie? What if firms use their power to sort of exercise and not participate in the if and only if contract unless they get the lion's share of the surplus for themselves? Those are all questions that we need to think about very carefully, and we can do that using game theory, but I won't do that right here.